So in the last two activities, we've been working backwards. So we've been working forwards this whole time, going from position to velocity, or velocity to acceleration. And now what we're going to be doing is we're going to be giving velocity, and we're going to try to work backwards to position. And there's two approaches that you can use. You can use this area approach that we learned in our last activity, what was it, 4.2.1 or 4.1.2. Or you can do this thing called anti-differentiate, which is, in my class, it was Eric's rule. In Mr. Pardun's class, I think it was Brent's rule. You could do that too. It kind of depends on what you're given. So let's review a little bit. If we have a positive velocity, that means our position is going to be increasing. So with a positive velocity, imagine that in your mind right now. You have positive y values in the velocity curve. That means that the position is going to be increasing. So we're going to dig into some examples of negative velocity where the position is decreasing, but for right now we'll just keep it simple for you. We also had a constant velocity, and we found that the distance under the curve of the velocity was going to be our delta position, or our change in position. And that's a huge idea. The area under the curve of the velocity graph is going to be the change in position of our function. If we have an inconsistent velocity, meaning the velocity is jumping around, what we can do is we can estimate using rectangles, find the areas of those rectangles. We can estimate the area under the curve and the velocity. It won't be exact. It won't be definitely not as exact as the constant velocity, but it'll give us a good estimate of how far we think we've traveled. Finding the area under the curve is a useful exercise. It allows us to go from velocity backwards to position. So here's just a little recap. I'm going to show you two graphs. So first of all, you'll notice this is the velocity graph. The area under the curve is going to be the change in position. So the area equals 3 miles per hour. That's going to be your y value, times the number of hours you travel. That's going to be your x. And we get 3.75 miles. Notice that this is cool. The units will cancel out because we have hours in the numerator and the denominator, so they'll cancel out. Now let's work backwards. Let's anti-differentiate this function, and we get this graph right here. And if we wanted to find the change in position, just like we did, we would say, okay, s prime of t equals 3. S of t equals 3t. So s prime of t is the same as v of t. Those are interchangeable. If I want to find my change in position, I just find s of 1.5 minus s of 0, and I get 3.75 miles. So we say s is the antiderivative of v. So this is my v right here. Taking the antiderivative will bring me my position. S is the antiderivative of v. That is a huge, huge concept that we're going to really dig into second semester. So this is something I mess up all the time because I write in all capital letters. But whenever you see a capital G, if you have a little lowercase g, the capital G is going to be the antiderivative of lowercase g. So that means that G prime, capital G prime, is equal to G. So imagine you have G right here. If I take the antiderivative of little g, I get big G. And if I take the derivative of big G, I get G. So for example, if I have g of x, so again, this is our original function. We're going to take a step back. We're going to anti-differentiate it. So Eric's rule, you go ahead and you add 1 to the denominator, you add 1 to the exponent, and then you divide the coefficient by the exponent. So this is our antiderivative of little g is big G, and you get x cubed plus x squared. They're antiderivatives because g prime is equal to little g, but I know what you're thinking. There are multiple. There's actually infinitely many antiderivatives that have this as a derivative. So watch, when I take the derivative of h, I get 3x squared check, plus 2x, check, and then the derivative of a constant is 0. So you can pretty much have any constant you want. You can't pretty much. You can have any constant you want at the end of your antiderivative. Okay, cool. You got an activity to do. 5 minutes, pretty good.